I want to thank all of you here for attending this morning, and thank you for the invitation to speak. I'm going to probably go through the first part of this talk a little bit quick because I really want to focus on the last part of the talk with respect to mechanotransduction and some surface technologies. But I'm going to present some new and innovative biomaterials and surface textures and technologies. A lot of it will be focused on orthopedics, but you'll be able to see it kind of applies to many different areas of medicine. These are my disclosures. I am the owner of Orthokinetic Technologies, which is a consulting firm, and Orthokinetic Testing Technologies, which is an A2LA accredited medical device test facility. To give you a quick overview, I'm going to go over innovative biomaterials with respect to implant performance and the challenges that we face in this industry, and how surface structures and textures can affect cell behavior and responses, in particular with implant development work. I've probably spent the last few years, currently after I left my academic position, working with manufacturers and surgeons and engineers with respect to developing implants that can have longer lifespans in the body. So we'll start, obviously, with the definition of biomaterials. It's a material intended to interface with biological systems to augment, treat, or replace damaged tissue. The goals are to replace the component of living tissue, to restore function, to really have a harmonious interaction with the host, to achieve long-term biocompatibility within a living system, long-term structural integrity, and to allow for tissue to substitute for that material over time. That's a huge, huge set of goals. We're not there yet. We're getting there, but we're not there yet. This I put in here because bone really is the ultimate biomaterial. Why? Well, it's light, it's strong, it can adapt to its functional demands, and it can repair itself. It's really a dynamic living process. As it breaks down, it rebuilds and remodels over time. And it'll do that differently depending on lifestyle and diet and health conditions and age, etc. And of course, as you all know, there's different types of bone throughout the body that have different mechanical or biomechanical thresholds and functions, and they can have different failure thresholds as well. Wolff's Law, you may be familiar with, was formed in 1891, but basically its form follows function. Bone responds to mechanical stimuli. That's why they tell little, as we age, I didn't want to say little old ladies because that's going to be me, to make sure we exercise. Why? So that we can load our bones and we can develop and grow more bone in response. So bone will respond to mechanical stresses by either laying it down or taking it away. So we're faced with what materials will really mimic living tissue. Well, there's a lot of challenges, as you all know. Fixation and stabilization at the bone or tissue interface for any device is a major challenge. We are seeing this currently in the hip industry, metal on metal, osteolysis, wear debris, another major challenge when we're trying to develop mobile joints with the materials that we currently have on the market. Of course, we deal with organ systems. They're a complex network of composite tissues and structures. I spent the initial part of my work in the area of spine. Well, a vertebra is a very complex joint, for lack of a better term. You've got a bony facet joints, and then you've got soft tissue, and you've got ligamentous tissue, and you've got 6 degrees of motion. So it's very difficult to mimic that with implantation. So I'm just going to run through a lot of kind of new materials out there. There's so much going on in biomaterials. It's a great time to be in material science, basically. There's nitinol and new versions of nitinol, exciting versions, foams or metallic foams. There's resorbable metals, and I'm going to give you a quick slide. Magnesium is making a comeback. It is a resorbable element and metal that they're starting to look into again for implants. There's titanium fibers and meshes and foams. The nice part about titanium is it's fairly inert within our body. However, now it's currently machined, and there can be issues if you notch it or you have any type of stress riser. It will not fatigue well if there's a notch into it and any kind of defect can cause earlier failure. But now you can actually 3D print it. It can be woven into meshes, et cetera. And so we're developing much more complex forms, and I'm going to show you a slide later on of a titanium 3D printed cage. There's porous tantalum. This is a Zimmer product, believe it or not, that they're the ones that basically have the tantalum for orthopedic devices. And then, of course, there's new hydrogels and resorbable polymers. LGA, they had a bad rap early on, but there's new polymers, resorbables that are coming about with a gentler, kinder environment. But there's a lot of work that needs to be done. And finally, smart polymers that actually have viscoelastic properties that could mimic tissue from a mechanical aspect. This is the tantalum I was telling you about. It's trabecular metal. It's touted as resembling bone. It's an elemental tantalum. It has an 80% porosity, and it allows 2 to 3 times greater bone ingrowth than conventional titanium and or PEEK. It has a high coefficient of friction for better resistance to motion and pullout, et cetera, with an increased shear strength. It's expensive, I believe, and it has a pretty expensive manufacturing process. Hydrogels, as you know, are used in joints for soft tissue shock absorption. They imbibe fluids. They become gel-like. You can put it in as a hard plastic. It'll imbibe body fluids and become very gel-like, and you can control that durometer. It's used for drug delivery systems as sealants, as scar barriers. It's used in diapers and contact lenses, and you can use it to build scaffolds for cell growth. Again, some synthetic gels degrade into toxic chemicals over time, but some natural gels are mechanically weak. A lot of work is being done in this area, especially in drug delivery, where they're putting in nanoparticles, silicon nanoparticles, for instance, to promote wound healing. Ceramics, again, another superstar making a comeback. It's not the ceramics of the old days. They're stronger than metals. There's new and innovative ceramics coming out that are very durable. They have a very high stiffness, and everybody always thinks in orthopedics, oh, high stiffness is bad. It's not about the stiffness. It's all about the stress that gets transferred to and from the bone interface. So obviously, if you change your geometry, if you increase your footprint, you can decrease that stress, and you can minimize stress risers that can occur and cause earlier failure. But these new ceramics are being developed so that you actually have multiplanar strength and durability and less brittleness in the different planes. This is a porous silicon nitride ceramic, and as you can see, they have both a cancellous. The porous is really representative of cancellous bone in the body, and then they've got a denser one to represent cortex. And on the right, let's see if I can get this. They've done some animal work where they've got the silicon nitride, which is a very inert material in the body. And this is Amedica's product, and they've shown that you're getting bone growth into that porous silicon nitride quite well in sheep vertebra. Finally, nanofibers and nanomembranes. Nanomembranes can be protein-based. They can be synthetic. They act as sieves and filters and for wound care, for instance, and scaffolds. But the nanomembranes are being used for a number of different medical applications. Artificial pancreas, for instance. A nanomembrane can function as a sieve to let good molecules in and keep out the bad ones and vice versa. And then they have nanofibers, which are being spun at the nano level, and they can all be seeded and form as matrices. Some actually are stretchable fibers that they're made out of, and they're putting them into textiles. They've got smart textiles now. So there's a lot going on in this area as well. And combining all of that can really make for a very interesting cutting-edge medical device. Pyrocarbons and nanocarbon films, we've done a lot of work on the nanocarbon film area. They're used for joints. They're beautiful for load-bearing or mobile bearing, joints, because they're very low wear. It is biochemically inert in the body. The body does not really react to nanocarbon because we are carbon. Very, very high wear resistance, very low coefficient of friction. And then now there's so much work going on in infection resistance and antimicrobial materials. Ceramics have actually been touted as antimicrobial. Silver's being infiltrated into polymers. We have in the United States a very high infection rate, and so it's become kind of a focus of a lot of device companies. Resorbable biomaterials is a material intended to interface with the biological system. It's designed to slowly resorb to allow for tissue substitution. A smart bioresorbable material will respond to the changing stimuli. But there's a lot of challenges with these implants. From a regulatory perspective, they're difficult to get through clearance in today's day and age because of things that have gone awry in the past. So you really need to understand the in vivo environment you're going to use them in. You need to understand that they really are dose specific. If you have a large resorbable plate versus a very small resorbable screw, you may have a lot more leaching compounds or toxic byproducts that can develop in that local tissue. The mechanical integrity can be compromised if your material degrades too fast. So you really have to understand, how do you balance that rate of degradation or resorption of the implant versus tissue substitution to maintain mechanical integrity. This is an example of the bioresorbable magnesium. We had done some testing. What I liked about it was it's an interesting material because it actually fractures under compression, much like that of bone, especially cancellous bone, which will stack upon itself as you compress it. But it does have the elastic modulus, about half of what you see for titanium and stainless. And then, of course, is bioactive composites and bioceramics that have shown successful attachment to the connective tissue. They can be osteoinductive, osteoconductive. They can allow for tissue substitution. And they try to mimic that tissue environment. But we've done some testing in this area as well, and they can tend to be brittle as well. So we're looking, currently there's companies out there that have cleared screws on the market that are biocomposites. Now take all of these biomaterials, and I'm going to leave you with the one message. It's not just about one factor here. Everybody goes, oh, if I change the biomaterial. It's about the material that you're using, the design, understanding the cellular interaction, understanding your interface. So as we move into surface textures, we can't talk about textures without talking about mechanotransduction. So I'm an engineer by training. I'm not a cellular person, so forgive me if my cellular discussion is a little too brief. But surface textures can actually induce mechanotransduction. They can guide cellular growth. They can increase cell proliferation, or they can increase cell efficiency. Sometimes you don't need to increase your proliferation to increase the efficiency of the cell or the performance, the function. And we've used them on metals. Often they'll take titanium rods for implants and they'll surface treat them. They may shot peen them to improve its fatigue resistance. And may roughen it up to improve its osseo-interdigitation so that you get better fixation at the bone interface. So let's just quickly define mechanotransduction. It's the process where mechanical energy is converted into electrical and biochemical signals. So you subject an implant or the tissue to a mechanical stimuli, and you actually have that stress or load transferred to the cells, and then the individual cells will actually respond with what we call cellular mechanotransduction, where they convert these mechanical signals into some sort of biochemical response. Cellular mechanotransduction is seen in all eukaryotic cells. They are mechanosensitive. There's a lot of research being done on the biomechanics at the cellular level now, which is really exciting. It will take the forces, gravity, tension, compression, shear, and those forces that are transmitted at the cellular level will actually influence that cellular behavior. And they respond in a way by generating internal forces from the cell cytoskeleton to respond, and often they respond by generating contractile forces. The mechanism of action is these cells that adhere generate tensional forces. They're actomyosin-based contraction. And then they exert these forces to the surrounding cells and the extracellular matrix. the most interesting part of this, because I'm going to show you a slide later on, is if they lose their shape and they're not adhered to that living tissue, for instance, if they're round, they may be less efficient. If they spread when they're under tension, they may not proliferate as much because they take up more space, but they function in a much more efficient manner. And so you want to try to prevent overstressing the cytoskeleton of the cells, for instance. So looking at evidence of mechanotransduction, well, I kind of gave you a quick example earlier where I said a lot of titanium may be shot blasted to improve its fatigue resistance. This study actually looked at taking, this is an old study, shot blasted rods, and they compared it to titanium rods, which came raw form, and then polished, which is how they used to prepare them for implants. And then they looked at the endothelial responses, and they found that the shot blasted, which had a much rougher texture on the titanium, actually had an exponentially significantly greater response to endothelial attachment to them. Using additive manufacturing, the titanium may come out very, very rough, and we've done a lot of testing in this area. But cells, especially osteoblasts, love that. They love the rough surface. They love that interdigitation, which is great because if they recruit the osteoblasts to come, you get better fixation, earlier fixation to the surface of that roughened titanium. And then the bone grows into the crevices and you get better long-term attachment. And you can see the difference versus smooth machined titanium alloy here. You're not going to have as much attachment. This is some work we had done at the Cleveland Clinic when I was there. These are 10 micrometer posts on polymeric matrices that were, they're microstructures that were fabricated on PDMS. And what you're seeing is the chondrocytes here, they had different posts and then ridges, but this is the post study. The chondrocytes had the biggest affinity for the 10 micron size posts. That was the optimal size for that specific cell. And again, looking at the ridges, you're seeing these cells really grow along or within the grooves of the ridges here, and that's their preferred orientation, and they're spread well. In another example, this is microstructured posts again, and this is a fibroblast. And if you notice, it only grows on the surface of those posts, and it spreads itself out for, again, better efficiency. And you can make these microstructures and now nanostructures. At the time, these were microstructures. That was the latest and greatest. I did my work in MEMS. But now they're bringing it down to the nano level, and by seeding them, you can actually basically program and direct your cellular growth as well. There's a lot done in microfabricated pores and channels in polymers, as well as metals and others, where, again, you can program. Lab on a chip is a perfect example now. You've got a small chip, they've got pores so that they can do instant blood analyses, but you can direct the proteins, the molecules, to where they need to be and program the response and program the function. This is courtesy of NanoV. It is a nano surface out of titanium. Now, we talked about roughened titanium. Cells, osteoblasts, like roughened titanium, but they really like a repetitive porosity more. We see this in the dental world as well, all bone. So if you provide an ordered nanotube surface, which is what this, oops, my apologies, which is what this company has done, it looks much like that of bone, very ordered, very organized, versus conventional titanium on the right. The interesting part, where I bring you back, is on the conventional smooth titanium that's machined, the osteoblasts attach to that surface, but look, they're balled up, they're tightly balled, versus with the nanotube surface, you've got a lot of repetition here, but you've got a cell, an osteoblast, that's well spread. It basically has shown to be much more efficient with respect to its responses and attachment. And this is one of the large animal in vivo studies they did to further demonstrate this. So you can see with conventional titanium, you've got a lot of fibrous tissue around that pedicle screw. This is a pedicle screw used in the spine for fixing the spine, fusing it into place for pain. Well, this is in a good situation because eventually that screw is going to come out. It's going to cause too much micromotion. You may not fuse, you may not heal that joint, and the patient may get worse, and the doctor's going to have to go back in and refuse. But with the nanostructured surface here, you're seeing beautiful bony apposition up against that nano titanium surface here. And this was further demonstrated mechanically where their pull-out forces were significantly and exponentially greater. This is work we've done with a group of folks where it's a simple surface finish to titanium, to stainless. Actually, we looked at a number of different metals to improve bone contact. Instead of taking a conventional helical screw, they've got a specific geometry, and it applies minimal compressive stresses to the bone interface. Amazingly, because I wasn't a believer at first until we actually tested this, and we've worked with them for a number of years. It has an incredibly low insertional torque. Counterintuitive to what surgeons think, right? If you go in, if it takes a lot to turn it, and if it squeaks, it's in there. That's not always good for that bone interface. That could be a very bad thing, especially in dense cortical bone where you can cause microfractures. With a low insertional torque, if you have a convoluted fracture, for instance, you want to be able to go in with a low insertional torque into this dense bone, minimize the risk of fracture fragmentation. But you're getting greater compression force across that fracture site. And this is just one of many studies that we've done. But we found that this is severely osteoporotic human bone, where I placed a sensor to look at the compression force that this type of screw has. And it showed that you're getting much earlier compression at a low insertional torque at higher loads. And finally, you can develop with 3D printing, additive manufacturing, complex truss structures and matrices here. And this is a cage. There's a number of long bone ankle devices that are now cleared. Out of titanium, it has a roughened surface, but it's a truss structure that actually has incredible multiplanar stress distribution throughout the implant. Most of the earlier implants would have stress distribution uniaxially, just along the length of the hole in the middle of the device, basically. This is distributing it across the entire device. Titanium is stiff, we talked about this, but if you've got a stress distribution throughout the implant and across a larger footprint, guess what? The stress transferred to that surrounding bone is much lower. And what we saw was earlier remodeling in sheep because of these multiplanar stress distributions. So for the future, improved biomaterials may provide greater synergy with that tissue for increasing that implant lifespan in vivo. The surface textures can guide cellular responses, growth orientation, and differentiation potentially. And additive manufacturing, combined with these as well, can create that open complex structures. It can create composite structures, much like that of bone, for tissue ingrowth, cell seeding, and implant replacement. I wanted to acknowledge the two companies for contribution of these slides, as well as Medical Facets for contribution of the slide with respect to work we had done. And thank you for your time. I guess I'll open up the floor to any questions. Yes.
I'm Dr. Emre Karadeniz from Turkey. I want to ask two questions. The first thing is, do you have any experience about magnetic active materials in vitro magnetic active materials?
Magnetically active?
Yeah.
Yes. They have some devices out for leg lengthening,
Yeah.
Scoliosis,
Yeah.
and even brain for hydrocephalus, for instance. With respect to the leg lengthening, I think it's fantastic. They're actually cleared in the United States, and you know it takes us a lot longer here because of our regulations. And we had done a lot of work there. And with respect to that, they've done quite a bit with the magnetic part of it, and then you have to do a large series of testing to validate that it's going to be safe long-term for the tissue as it heals and grows. Now, these type of devices, and especially with scoliosis in idiopathic scolies in adolescents, you can go in and take the implants out, and you may want to. So the lifespan isn't as long as what's needed for, say, an artificial hip, for instance. But again, it's real promising to know that those are currently on the market, as is the scoliotic devices, where you can change the fixation and the length, for instance, just through magnetics and not having to go back in and do surgery again, because that's can be just as detrimental to the patient.
What is the material? Do you coat them, or there's a material which is magnetic active?
That's a good, most of that's proprietary. When they make the implant, though, the implants are made out of conventional, most likely titanium. Most of them are titanium and stainless. But the device that does the magnetic actuation is pretty much proprietary to us as we're testing it. And there's different designs out there, but they would probably put it in a hermetically sealed containment unit on the device itself.
I'm asking this because I've got an innovation about this implant technologies, and we got to use magnetic active materials in the body, and we are trying to coat them or make a magnetic active material. But in Turkey, we could not be able to find the exact answer. And we asked for American companies, and they did not give the true answer for us. And tomorrow I will present the innovation to you, and I think we could get information.
Well, I think so, because it's interesting. You're fortunate to be able to do that before we could. So to put magnetically active material exposed, for instance, is a much more rigorous regulatory challenge in the United States. Yeah. But I'd definitely be interested in speaking with you.
Thank you.
Sir?
Yeah, my question already. I was wondering if you could perhaps spare a few minutes on what you think could be the current challenges for the design of future biomaterials, and where do you see that advancing or developing in the future?
Ooh, there's a lot of challenges, and the biggest one is balancing. So I think sometimes folks come out with the material before they know the actual application. That's difficult. Really what you want to do is pick your problem and your region, because your material is going to have to be so different from a mechanical, chemical, physiological situation. Understand that region and say, okay, what do I need to really improve this condition here? And then maybe work backwards with understanding the materials. So one of the current challenges is the ability to have materials in our body long-term. And there's a lot of inert long-term materials that can exist well, but they're simpler structures. Where I see it advancing more is the ability for the materials to resorb and allow natural, normal tissue to come in and substitute, because that's the best way. Our own tissue, regardless, is always the best way. And so if we can get to that point where we can control it a lot better, and I'm a big fan of nanomedicine. I think that with where we're headed there, for instance, they've got cantilever beams at the molecular level that can detect cancers at such low rates that it could actually be curable. So if there's a way to start to think about how can you somehow know that your material is performing the way it needs to perform in the body, and maybe that's a mixture of new technologies such as nanotechnology with a material for that specific region, and really address and are able to address the chemical, the physiological, and the mechanical for that region. It's tough because folks come out with a material and they go, okay, I wanted to do everything. It's not going to do everything. It's not going to do everything well. So part of where we are at is, I'm a huge fan and major proponent of always work as a team. And especially with what we do, I get to see a lot of things, and I like to marry people. I should have been a matchmaker. I like to marry technologies, because company A isn't going to really know what company B is doing. But that's not going to help the future of medicine and implants. It's really about understanding, company A would be a wonderful partner with company B if they developed this. Now their product, now their material has a lot of value. So, but I think the best would be is if we can develop a totally inert material that can change dynamically, i.e. Viscoelastic properties. So they can have different responses to different strain rates, for instance, because that's how our body works. But we age, and when we age, our tissue stiffens. So we are dynamic creatures, and if we can find a material that can do that, is inert, or maybe it goes away in a manner that the tissue can come in and replace it quickly and organize itself in a normal, that's the ideal situation. We're not even, we have a ways to go. Thank you.
If you talk about arthroplasty surgery in orthopedics, a material must be inert and interdigitate to the bone. That's the truth. But about osteosynthesis surgery, if we are talking about inertity, that's true. If we don't take out the implants, it will be a problem for us. But in osteosynthesis surgery, our implants must interdigitate to the bone. I'm asking this because screw cutout or implant failure problems are not too much in healthy bone. And do we need to enhance the interdigitation between implant and the bone in healthy person?
I think so, if I understand. So let's take the hip, perfect example, right? So in the United States, we have a major problem, osteolysis from metal debris. That's because early on, part of it is metallic debris is nanometers in size. Well, years ago, we didn't have capabilities to assess nanometer. We assessed from 1 micron and above the particulate sizing. So you're missing that correct bandwidth. With that said, a lot of that is, you're going to have motion for a number of, you're going to have debris for many different reasons. Part of it is if it's not clocked appropriately and you're eccentrically loading that implant, you're going to have greater wear. Let's take that out. Let's just assume it goes in perfectly. You want to make sure that you get great interdigitation fixation at that bone interface for the stem, not for the mobile part, but for the stem. Why? And early on. Because if you get it early on, you now have a stable device. There's no micromotion from the neck down into the stem. So basically, your device is going to operate. It's really more about the wear. It's stable, and you'd probably have less wear. When you start to factor in micromotion, you get bone breakdown, you get more osteolysis, which then it's a cascade, more breakdown of the bone. And you're right, you have to go in, now you have to take more bone out. What are you going to do? What are you going to do in this person who's had this implant in for 10 years and you don't have a lot of bone to fix to? So you're going to have to keep going further down. I mean, there's a lot of problems with that. And it's harder when they take someone in their 40s or 50s that have to have a hip or knee implant, well, hips mainly, had a hip implant. They've got a lot of years left, and hip implants aren't meant to last forever. But
I'm especially asking this question to the osteosynthesis surgery.
For fusion, is what you're
for
saying.
fusion.
Fusion is, yes, because in the spine, which is where I started my life, fusion is an issue. It's an issue for, of course, many different factors. Diabetic smokers, hard to fuse, right? So you need to make sure you make that segment biomechanically sound, biomechanically rigid, if there's any kind of micromotion, that diabetic smoker most likely isn't going to fuse. They're going to have pseudarthrosis. They'll have fibrous tissue around their cage. With fibrous tissue, it might be stable, but if it's not, over time, that motion increases because there's substantial complex loading across the joint, and your hardware that's put in will eventually fail, because even though you test them in fatigue, their bone is always your weakest link, and well, yeah, the bone and the hardware over time is eventually either going to break or the screws are going to come out. So it's really about gaining that stability early on. And now what I like about that spine cage I showed you here, when we first looked at this, again, this was one of those, no way, when I got the animal work back. Didn't believe it. I was pretty amazed. And we need to get going. I'll go quick and just say, the interesting part is we started to see, we think we're seeing earlier fusion. Well, from the outside in, that's a good thing because it's like taking fingers on a chain link fence and hanging on. You've got better stability than just having your pinky finger hanging on, which is indicative of some of the spinal cages you may see with the big core in the middle, because osteoblast bone doesn't like some polymers. So there's a lot of different factors that come into play, and the multiplanar stress distribution allowing for earlier fixation can provide earlier stability, which can actually improve that cascade or the health of the implant long term. I hope that addressed.
Thank you very much. So later we can interact during coffee. Right now we have to start the next session. So thank you very much, Professor Ferrara.
I'll do that, just like you did.